No questions? Okay. Okay, great. So last time we introduced ourselves to the concept of phase, which was basically a chunk of material with everything same, no distinguishable physical difference. Composition, magnetic moment, density, anything and everything you can think of looks the same. And then we talked about the concept of a phase transition, which is that given two phases for a material or any chemical, alpha and beta, if G alpha minus G beta is less than 0, then at constant T and P, alpha will be dominant. Alpha will be the phase, let's not call it dominant. Then at constant temperature and pressure, alpha will be stable phase. And similarly, if G beta minus G alpha is less than 0, then beta will be the stable phase. You move in the direction of lower Gibbs free energy at constant T and P. And I showed you the example of a phase transition, which was nucleation or solidification. There, the free energy, I constructed a model where delta G looked like AR square minus BR cube. And you have to, or you could write it minus AR square plus BR cube, whichever way you want to write it. The idea being that the free energy dominates for the new phase to form, but there is a surface energy term which goes as the surface area of the new phase, of the boundary between the two phases, which has a cost. And if A is positive and B is positive, then in this regime, this curve delta G versus R looks something like this. So what it means is that liquid will be favored here, then solid will be favored if you have a nucleus bigger than a certain size of R star, you will form a solid. So in this case, you can say that G solid is less than G liquid, because once you have a material, you have a box of liquid where this critical radius would be just something like this, something very, very small, much smaller than the box size. So at some point, you can see if the whole box became solid, then the free energy of the whole box is going to be lower than the free energy of the liquid. So it is favored. This is the spontaneous change, direction of spontaneous change. However, it is not instantaneous because there is a barrier that needs to be crossed. You need to go above this barrier of the critical size of the nucleus must be bigger than R star for this to happen. So even though it is spontaneous, you might have to wait for a very, very long time for it to happen. But that's the example of a phase change. And there can be many, many different phase changes. So this was just an important reminder to you that kinetic effects matter. And in the last two classes, I think we will talk a little bit about kinetics. But something we tend to ignore in thermodynamics is that just because something should happen, it doesn't mean it will happen even in the age of the universe. You might have to wait a very, very, very long time. So we introduced phase, we talked about phase transition. The next thing I want to talk about is the concept of a component. Normally, component is denoted by the letter C. It is kind of like the composition, but not quite. What do I mean by that? So the definition of a component is that it is a chemically independent constituent of a system. It is a chemically independent constituent of a system. What does it mean? Another way to think about it, it is the minimum number of independent species required to define the composition of all phases. So it's defined quite rigorously over here, and it gets complicated. I'm not going to get too much into calculate. I will not be giving you problems where I have you calculate the number of components in a system. It gets complicated. I will tell you the recipe, and for any problem, I will specify, take it as a one component system or a two component system or a three component system. And I will show you why it gets complicated. So almost always, this is simply the same as number of distinct chemical species. Almost always. What do I mean by almost always? That once in a while, it is not true. When is it not true? For example, if there are chemical reactions happening. If there are chemical reactions happening, then you have to subtract out the number of chemical reactions that might be taking place. If there are any constraints on the system, for example, charge neutrality or something else, that also needs to be subtracted out. Number of constraints. What would constraints look like? They would be, for example, charge, neutrality, or molar balance, things like that. So almost all the time it is number of distinct chemical species. So if you're looking at a water phase diagram, water is the best example here. If you're just looking at water and we are not considering autocatalyzation of water or something like that, minimum number of independent species required to define the composition of all phases. So if you're looking at water, no problem, then number of component is one. There is no reaction taking place. I have not given you any constraint. It's just one. However, on top of that, I tell you that water is undergoing this autocatalyzation of water reaction, which is 2H2O. So let me write it down. Just water, C is equal to 1. However, if you have 2H2O going to H3O plus OH minus, in this case, C will be 3 now because the number of distinct chemical species is H2O, hydroxyl, and hydronium, right? However, you have a chemical reaction going on, 1, and you also have a charge neutrality constraint, 1. So it again comes down to 1, but for the wrong reason. That, not wrong reason, but a reason you might not have thought possible. If CaCO3 is going to CaO plus CO2, what can we say about C over here? The number of distinct chemical species is again 3. The number of reaction is 1, but we don't have any constraint here now on charge neutrality or anything like that. So the number of components is 2. So this gets messy. You might say, well, what about molar constraints here, this or that? So I'm not going to go, like I said, too much into components. But in the papers that you're reading or in your research or otherwise, you might come across this. And this is something to be careful of, that you always start with number of distinct chemical species, and then you have to reduce from there in order to get to number of components. So what have we talked about now? We have talked about phases, and we say that the number of phases in a system we are going to denote as P, and number of components in a system as C. Okay, these are the two things we have introduced so far. And with this, we are almost ready to start talking about phase diagrams a bit carefully. And the two things that I want to do today is to tell you about, given the number of phases and given the number of components in a system, what can you say about the phase diagram? Is it going to be a line? So for example, I have the water pressure temperature phase diagram, and I want to ask you is, so here there is water with just C is equal to 1. And I am asking you, if liquid and solid were to coexist, would it be a point, would it be a line, or would it be a whole area in which they could coexist? It's not an obvious question, right? Can anyone think of an obvious way to answer this without invoking Gibbs phase rule? If you can, tell me on Slack or tell me now. Can anyone think of a way why this is obvious? Which one of these is correct? Okay, if you think of one, then stop me later and tell me, but I can't think of one. And it turns out that they exist along a line. This one is the correct answer. This is wrong, this is wrong. And along a line, it means you have 1 degree of freedom, right? A line, so the next concept we are trying to bring in here is the number of degrees of freedom, which is denoted as F. And the rule that I'm going to derive today is that F is equal to C minus P plus 2. So if C is equal to 1 and P is equal to 2, then 1 minus 2 plus 2 is equal to 1. The number of degrees of freedom is 1. And that is in a 2D plane, 1 degree of freedom means a line. In a 3D plane, it might mean something else, but in a 2D phase diagram, 1 degree of freedom means you can only vary one parameter at a time. If you had F is equal to F is equal to 2, then you would have had a whole surface. So for example, if you're talking about a single phase region, only liquid, and if single phase region, then we have P is equal to 1. Again, we are talking about water for now. C is equal to 1. So C minus P plus 2 is equal to 2. And the single phase region will be some area. It won't be just a line. And if you're talking about a triple point of water where all three phases exist at the same point, triple point has P is equal to 3. Then F is equal to C minus P plus 2 is equal to 1 minus 3 plus 2 is equal to 0. No degrees of freedom, it's going to be 1. So I already mentioned to you that water has the number of degrees of freedom in the line point. In the diagram, it's not related to the number of degrees of freedom that we did earlier in equipartition. No, it is degrees of freedom in this curve, in this map, in this pressure temperature map. What are the degrees of freedom? That's a good question though. We are not talking about the equipartition. Now let me ask you, I told you water has more phases, right? There is liquid, there is ice 1, there is ice 2, and so on and so forth. Is it possible that in a pressure temperature phase diagram, liquid, ice 1, ice 2, and ice 3 exist at the same point? Is it possible? Any answers? Okay, I got Joyce. Joyce, why not? You want to unmute yourself and enlighten us? Or just type it out? Joyce doesn't want to tell us. Anyone else? It's okay. Ice 1, ice 2, ice 3 are phases of ice. Ice can exist in 15 different phases. They are all solid, but the crystal structures are different. So why did anyone wants to tell me as to why do you think this is not possible? In a pressure temperature phase diagram, why can't you have 4 phases existing at the same point for water? What would it mean about F? F would be 1 minus 4 plus 2 is equal to negative. Negative degrees of freedom makes no sense. You don't even have a point. So this is already deep insight that in a pressure temperature phase diagram, you cannot have 4 phases existing at the same pressure and temperature. It's simply not possible. They simply cannot coexist. They cannot be an area, they cannot be a line, they cannot be a point. If you had a third axis, if you were talking about different degrees of freedom, maybe there would be some other thing that's going on. But basically, the number of degrees of freedom here it's not possible for them to coexist. So we haven't derived this yet, and we are going to get this in a moment. So pressure temperature diagram can only represent 1 degree of freedom always? No. In a pressure temperature diagram, 1 degree of freedom means a line. This is 1 degree of freedom. 0 degree of freedom means a point. 2 degree of freedom means an area. Okay? You can't have 3 degrees of freedom because you have only P and T. What are the number of things that you can vary at the same time? Number of degrees of freedom. Degree of freedom is number of variables that can be independently varied. And we are talking solely about pressure temperature. Yeah. Yeah, and Kate explained it to Elizabeth. That's what it is. You know, it's different phases of ice, you know, and you can go to a phase diagram. In fact, I had one of them open. This is the phase diagram for iron carbon system. It looks so complicated and it's super important. Like any, this is a temperature composition phase diagram. And as you start to add small amounts of carbon in the iron carbon phase diagram, new phases start to appear. Here you have sort of like a triple point or something where multiple phases exist at the same time. And it goes on and on. When I was an undergrad, I was supposed to remember this one and I always forget. And every phase has its own property. Similarly, you have a phase diagram for ice. So here you can see there are different solid phases of the iron carbon phase diagram. And in fact, when I was an undergrad, I went to a steel plant in India. You know, it's called a blast furnace where you actually make steel from iron. This was 2005, maybe, so 15 years ago. And I still remember there was an old man there who would work at the steel plant. He had been working there for 40 years. I think he was illiterate. He didn't know how to read or write. He could, however, look at the color of the flame coming out of the blast furnace and tell you the carbon composition up to 1 decimal digit accuracy. That was the level of intuition that he had. Yeah, you have quadruple points here also. The iron carbon phase diagram gets complicated because this is not just a one component system. You have reactions going on inside. So in iron carbon phase diagram, talk to the material scientists in the class. I know some of them are. Adam Feshler, where are you? You are a material scientist. You can tell others about it. So the material scientists are supposed to know this phase diagram by heart. We are not going to talk about it, but in the same spirit, you can look at the water phase diagram, which is also equally complicated because of the things that go on. Normally, we think of water phase diagram just like this one, very simple. We don't demarcate between the different phases of ice. But this is a more real water phase diagram where you can see the solid is so complicated. Orthorhombic ice. You know, next time you go to a party or something, or someone asks you, would you like some ice in your water? You should be like, yes, but I would really like only orthorhombic ice. You think you're a mega nerd. So it gets very complicated. These are all solid phases of ice, and you can see they start to show up under very low temperature and typically high pressures. That's when they start to show up. And it matters for a variety of applications. So the thing that I want to talk about next before I derive Gibbs phase rule is to look back at our chemical potential, because that is really the key to understanding this Gibbs phase rule and the remaining aspects of phase diagram. So we can express our second law of thermodynamics. Any more questions? If there are any questions, please type it out or just unmute and ask. We can re-express, as you must be getting a feel so far from thermodynamics or PChem, it's really about re-expressing the second law of thermodynamics in a variety of different ways. And if you integrate it to the first law of thermodynamics, then you're done. Then you have all the information that you need. And it's all about making it useful, making it applicable to practical scenarios. You can always just work with delta S total more than 0. And that is correct. But if you have constant temperature pressure, it makes sense to think about Gibbs energy. And that's what we're doing right now. So let's express second law of thermodynamics for phases, in context of a phase diagram. How do we do this? So in order to do this, let's suppose we have two phases, alpha and beta, both of which have different species. I mean, alpha can have all these species, beta can have all these species, 1, 2, 3, ... Okay, so what am I saying here is that we have two phases, alpha and beta, and alpha is made up of a certain number of 1, certain number of 2, certain number of 3, ... Beta is also made up of a certain number of moles of 1, certain number of moles of 2, certain number of moles of 3, ... It goes on and so forth. So the question now is, let's transfer a small amount of species 1. We could have done this for any other species. Let's just think of species 1. The argument applies in general. Let's transfer dn1, no, the small differential amount, dn1. And Thomas, we will get to quadruple points in a bit, I think. But yeah, you can have them depending on the number of components, right? Because if you have f is equal to c minus p plus 2, and if you allow your c to be large, if c is large enough, then you can allow p also to be large enough without getting into negative f, right? That's where it comes from. So for in multi-component systems, you can have quadruple, pentuple, I don't know, all sorts of complicated points. So let's transfer dn1 moles of species 1 from phase alpha to phase beta, okay? At constant Tp, at constant temperature and pressure. So if this change can happen under equilibrium, what does that mean? It means that the transfer of dn1 from alpha to beta is spontaneous, and also the transfer of dn1 from beta to alpha is spontaneous. In other words, for equilibrium, this change and its reverse both must be spontaneous, or dg should be equal to 0, right? You can't have dg positive or negative. It just must be 0, so that both sides, both type of changes, transferring dn1 from alpha to beta or transferring dn1 from beta to alpha, both would have the same free energy. So we can write this down as free energy change of alpha plus free energy change of beta is equal to 0. Now, if dn1 moles have been transferred from alpha to beta, what does that mean? That means dn alpha, the number of moles that changed in alpha, and keep in mind, we are keeping everything else constant. So the number of moles that change in alpha is going to be minus dn1, and number of moles that change in beta are going to be plus dn1 because it gained dn1 moles. We also have dg is equal to vdp minus sdt plus mu I dni, right? But pressure is constant, temperature is constant, and this one is constant or 0, dni is 0 for all i's not equal to 1. Therefore, dg is equal to dg alpha plus dg beta can be written as mu I dni for alpha, right? This term for alpha, actually mu1 dn1, because we don't care about all the other i's, we care only about one, I is equal to 1, plus mu1 dn1 for phase beta. We will write down mu1 in phase alpha as mu1 alpha multiplied by d1 for phase alpha plus mu1 for phase beta multiplied by dn1 for phase beta. I'm just writing it all in a formal way. It's not very complicated. If this is confusing you in any way, trust me, if you go back and look at it in 2 minutes, you will see it's just a formal way of writing something simple. What is dn1 alpha? We just wrote it down over here. It's equal to minus dn1. So this is minus dn1. And this over here, mu1 beta multiplied by dn beta is equal to plus dn1 is equal to mu1 beta minus mu1 alpha dn1. And our condition for equilibrium was that dg is equal to 0 for all possible values of dn. What does this mean? The only way this is possible then is that mu1 beta is equal to mu1 alpha, right? because there is nothing special about dn1. Therefore, mu1 beta is equal to mu1 alpha for equilibrium. In other words, we have just shown that chemical potential of any species, we just showed it for species 1, but you could have done it for species 2, you could have done it for species 3. The only way to do it, the way to do it is to think about everything else being held constant. Therefore, chemical potential of any species must be the same in two phases that are in equilibrium. This is nothing but a restatement of the second law of thermodynamics. And this is why our chemical potential is so important, because as you will see, this notion will allow us to derive the Gibbs phase rule, which in turn tells us whether a certain number of phases in the phase diagram are going to be a point, a line, an area. If you're thinking of 3D phase diagrams, would it be a volume, and things like that. Is this part clear? Any questions about this? And I will generalize it as it is mu I alpha is equal to mu I beta for all I equal to 1, 2, 3, any species. We did it for species 1, but it will be true for any species. Any questions? Or is this absolutely clear to all of you? Okay. I assume it is more or less clear. If not, you can ask me. So that's interesting that at equilibrium, the chemical potential should be the same across, and we are talking about the chemical potential for a certain species. It is possible that mu1, the chemical potential of species 1 in phase alpha, is equal to chemical potential of species 1 in phase beta. But let's say we have chemical potential of species 2 in phase alpha more than chemical potential of species 2 in phase beta. So we had our two phases alpha and beta. And let's say the species 2, so it could be iron, carbon, nickel, and iron is the same chemical potential, but carbon has a higher chemical potential in alpha than in beta. What does this tell us about species 2, what it's going to do? So what I'm going to show you next is that species 2 will move from alpha to beta. In other words, mass transfer happens in the direction of lower chemical potential. And that is why we call it chemical potential. That is something which should not be profound to any of us, right? You are more likely to be sitting than jumping up in the air. You would perhaps prefer even more to lie down and just relax, right? Because you're loading your chemical gravitational potential is getting lower and lower. And that's why it's really called potential, because it represents the direction in which material moves. How do we show this? It's quite simple. We have, let's call it proof, but it's barely a proof, it's just an illustration. We have here mu2 alpha more than mu2 beta. And why did I take 2? Just for example, it could have been species 1, it could have been any species k. So if I have mu2 alpha more than mu2 beta, then this means that minus mu2 alpha plus mu2 beta is less than 0, right? I just took this one and brought it to the right hand side. So minus mu2 alpha plus mu2 beta is going to be less than 0. Or minus mu2 alpha, and I'm going to write it in brackets just for a bit because I'm going to multiply it by something. Multiplied by something dn2, both of them multiplied by dn2 will also be negative if dn2 is positive, right? Or mu2 alpha multiplied by minus Tn2 plus mu2 beta multiplied by plus Tn2 is negative. And that's all we were saying. Alpha phase would like to lose Dn2 moles of species 2. Beta phase would like to gain Dn2 moles of species 2. How do I know this? Because Dn2 itself is positive, and with mu2 alpha I have minus Dn2, and with mu2 beta I have plus Dn2. And this is the direction in which dg will be less than 0. In other words, if you have a difference of chemical potential, species will move from side A to side B. Chemical potential being equal means there is equilibrium. Any questions? It feels like, since because my screen is freezing less, now I can cover more material. It's good. All right. So now we are ready to start talking about the Gibbs phase rule. We are now ready for Gibbs. Oh, by the way, does anyone have any questions about the midterm of any sort? Has any group, is there any group here which is still arguing over which paper to read? No, you have all found consensus? That's good. Okay, so what are we trying to show here? We are going to try to show, and this is such an important rule that I want to write it again and again and again. It's really critical. F is equal to C minus P plus 2, where this is the number of degrees of freedom. This is number of components. And I showed you briefly today that number of components is actually complicated. It is related to the number of independent chemical species, as I wrote over here. Now, component is a chemically independent constituent of a system. It is the minimum number of independent species. So the thing is minimum, right? That's what it changes it. If it was just number of independent species, our life would have been simpler. Minimum number of independent species means that you take the number of distinct chemical species and you subtract out reactions and constraints. It gets complicated. We will be doing a bit of electrochemistry towards the end of this semester, and there you will see it gets complicated, and that's why I wanted to introduce this. When you do electrochemistry, you have to be careful with this. But if reactions are not happening and there are no neutrality constraints and everything, it's typically simpler. So we have number of components, and this is our number of phases. And this is super important because it tells us you can't have this many phases existing at the same time in a phase diagram, and that's really, really useful. So how do we prove this? We will do the proof in 2 steps. We will do it first for a one component system. It's not really a proof. I will show you why it makes sense for a one component system. And then I will do it for a general system with any number of components. I could directly jump to the second part of the proof, but then I think it becomes very confusing. So it's worth it to go through the first part where you have only one. So let's call it derivation, not proof. So case 1 is, we are going to do it in 2 cases. Case 1, when C is equal to 1, one component system, and case 2, when C is more than 1, okay? So let's first talk about case 1, when C is equal to 1, or one component system. In a one component system, we want to show F is equal to C minus P plus 2. But we have set C is equal to 1. So, right, so we want to show F is equal to 3 minus P. That's what we would like to show over here. How do we do that? Let's say if there is only one phase. If only one phase, then P is equal to 1. Or we would like to show what happens to F. So if we can show that only for P is equal to 1, F is equal to 2, then we are set for one phase. What does it mean? If it's one phase, then both pressure and temperature can be varied, right? Because nothing's stopping you. You have water, one phase water, you can vary the pressure, you can water the temperature, as simple as that. Therefore, F is indeed is equal to 2, which is 3 minus 1 or 3 minus P. So for one phase, it's trivially true. We didn't do anything. I just wrote down what it is. If two phases are in equilibrium, let's call them alpha and beta. Then what can we say? So now we have P is equal to 2. Can we now vary both pressure and temperature at the same time? If we could, then we are in trouble. Then our Gibbs phase rule won't be true. So what I'm going to show you next is that if you have two phases in equilibrium, then you cannot, in fact, vary both pressure and temperature independently. Why? Because as soon as we have two phases in equilibrium, now we have a constraint. The constraint is the one of chemical potential, right? The chemical potential must be same. Which chemical potential we are talking about? We are talking about one component system. So the chemical potential of that one component, chemical potential must be same. That is, i.e., mu of phase alpha at any given pressure and temperature must be the same as mu of phase beta at that same pressure and temperature. So we can no longer vary pressure and temperature independently because now we have one constraint. If we know something about the pressure and temperature here, and we know something about the pressure and temperature here, we can calculate their chemical potentials. There is some equation. We don't know what is that equation, but we are being given a constraint here that not all pressure and temperatures are possible for these two phases to coexist. Only those pressure and temperatures are possible which satisfy this equation. Therefore, one constraint exists, or knowing P can tell us T, or knowing T can tell us P. Why do I say that? Because we have an equation over here, right? This equation, it will look like something. Maybe it will look like P square plus T cube is equal to P square minus T to the power 4. It will be some equation. As soon as I put in the value of pressure over there, I can solve this equation numerically and calculate the value of temperature. So this is a constraint. In other words, number of degrees of freedom is no longer 2. We cannot vary pressure and temperature at the same time. Number of degrees of freedom is 1 here. 1 is the same as 3 minus 2. And in this case, P was equal to 2. So we again recover F is equal to 3 minus P. This is why I said it's important to the one component system first, because now when we go to the general proof, if you understand this part, the general proof will be easy. But this part is abstract. So I just want to take, I'm going to take like a 30-second break. I want everyone to look at what I have written and tell me if it makes sense or not. If it is confusing you, just say it. No one's judging you. Just tell me it's confusing you and I will go through this again. Take 30 seconds to read through it.
I have a question. So is this kind of, can we kind of think of it as like alpha and beta are in the same system? So like you can't change like the pressure of one and not the other because like they're in the same, like
Oh
you
yeah,
can't.
absolutely. Yeah. So good point. Very good point, Jared. We are assuming mechanical equilibrium. We are assuming thermal equilibrium, right? So this is an excellent point. Oh, thank you for bringing it up. I had really forgotten. when I say at equilibrium, and I will get to your question in a bit, Elizabeth. I should point out quite clearly that this equilibrium condition that I defined over here of mu being same is actually a third type of equilibrium that we had not seen so far. It is an example of chemical equilibrium. In addition, we are going to have mechanical equilibrium, which means pressure is uniform. And in addition, we are going to have thermal equilibrium, which means temperature is uniform, okay? That's why the pressure is same. You cannot have different pressure. If you have different pressure, then you don't have mechanical equilibrium. So excellent point. So let me write this down here. This is the condition for, see, that's why it's great that you guys ask me question, because I'm human, I can forget things sometimes. So this is the condition for.
Screen is frozen.
Yeah. I would say it's doing better than the past, right? In terms of freezing, it had really become terrible. Okay. So this mu1 alpha is equal to mu1 beta was the condition for chemical equilibrium. So just a bit of a recap from last page is that mu is equal to constant, or let's call it same mu is chemical equilibrium, same pressure is mechanical equilibrium, same temperature is thermal equilibrium. So when we say constant pressure and temperature, we are really talking about a material that is under mechanical equilibrium and thermal equilibrium. And now we are talking also about chemical equilibrium. And really equilibrium, we need to have all three. Okay, good. So Elizabeth's question was, how do you reach the conclusion that both can be varied independently for one phase? It's not a conclusion. I'm just saying we don't have any constraints and we are working in a pressure temperature phase diagram. So I know this sounds a bit funky and I'm surprised that no one asked me this earlier. So it's a very good point. I'm just stating it as an observation. It's not a conclusion, it's an observation that in the pressure temperature phase diagram, if there is no constraint, you just vary everything. That's the point. So it's not a conclusion, it's just a statement. Now I have a constraint that came over here. So here, if I knew the value of pressure in the top one over here, if I knew the value of pressure, any value of temperature is also possible. There is nothing telling me that there is a restraint. In this second one over here, if I know the value of pressure, not all values of temperature are possible because I have an equation that I can solve and get some limited values of temperature. There is a constraint. That's the idea. Okay, now Liam has a question. Do we only consider phases along a phase boundary? Or in the case of an isochemical system where the triple point exists and there are many phases, do you consider all potential phases in the PT space? No. What do you mean phases along? What do you mean by phases along phase boundaries? You can consider phases anywhere. A phase boundary is a coexistence of two phases.
Why don't
go ahead.
Sorry, I didn't mean to interrupt. Why don't I put this in Slack? I think it'll be easier to address outside.
It's a bit technical. You put it in Slack. Okay, good. And Elizabeth, the constraint is chemical, thermo, and mechanical. Thermal, not thermo. I guess it sounds similar. Thermal equilibrium. Yeah, you put that in Slack, Liam, and I will tell you there. But basically, no, phases can be considered anywhere. Phase boundary is coexistence of phases. So, here is the recap. Okay, so recap is so far is that same mu is chemical equilibrium, same P is mechanical equilibrium, same T is thermal equilibrium. And we are trying to look at the Gibbs phase rule for single component system. Let's finish that today, and next time we will talk about the general case. And so you can go over the single component system once again before you come to next class. So we have done 2 phases in equilibrium. Now let's talk about 3 phases in equilibrium. And we have to go to 4 phases, 5 phases. But what you will find is that you will see why it doesn't make sense to talk about 4 or more phases. So if 3 phases are in equilibrium, then let's say these phases are called alpha, beta, gamma. So we have P is equal to 3, and we are trying to figure out what is F, the number of degrees of freedom. So in general, F would have been 2, pressure and temperature both being varied, like we said for the only one phase case. But now we have two equations that we need to be careful for. We are going to say that mu, the chemical potential in phase alpha at any pressure and temperature, must be equal to mu in phase beta at any pressure and temperature, which must be equal to mu in phase gamma at any pressure and temperature. So we have two equations here, equation number 1 and equation number 2. We have two constraints. What does this mean about F? It means that F is now going to be 2 minus 2 equal to 0. Do you see why? Because when you have one constraint on pressure and temperature, you can solve for this and get a dependence, get a relation between pressure and temperature. But when you have two variables, pressure and temperature, and two equations constraining them, and you solve two variables in two equations, what do you get? You get a number, right? You don't get a relation. So if, let's just to give you an example here, if I have a relation such as 5x plus 4y is equal to 3x minus 8y, right? Where x is pressure and y is temperature, let's say. If I solve this, I will get x as a function of y, right? But if on top of this, I had a second constraint, that 5x plus 4y is equal to 3x minus 8y is equal to 7x plus 5y minus 3, or something like that. Then when I solve this, I will get the value of the point x and y where it is possible. It's possible that there is no solution. There is no x and y that meets this. In this case, there is no solution at all. But your degrees of freedom are not going to be positive now. You have limited. You are not allowing for x to vary or y to vary. That's the point. So F is equal to 0. What is 0? 0 is the same as 3 minus 3, right? Or again, 3 minus P. So we once again recover F is equal to 3 minus P. So this was for 3 phases in equilibrium. Let's push it one more step, and then we will see that there is no point in going further. How about 4 phases in equilibrium? If 4 phases in equilibrium, alpha, beta, gamma, delta, and again, recall that we are talking about one component system. Then we will have mu alpha is equal to mu beta is equal to mu gamma is equal to mu delta, right? So 1 constraint, 2 constraint, 3 constraints. Constraint is not the number of variables. Constraint is the number of equal signs that you have. We have 3 constraints over here. So if you think about F, that's going to be 2. That's pressure and temperature, right? Pressure and temperature minus 3 is equal to minus 1, which is nonsense. It's nonsensical. We can't have number of degrees of freedom being negative. Therefore, we have just shown that 4 phases cannot exist in equilibrium in a one component phase diagram. And we also showed that for 3 phases, for a triple point, the number of degrees of freedom is 0. So we just showed that the triple point, when 3 phases exist, why is it called a triple point? Because it's a point at which 3 things exist. So if you have a phase diagram, let me draw one and then I'll just stop, in pressure and temperature, which looks something like it has some points, it has a line over here, and this is really a practice problem for you to think about this. I'm going to start with this example next time. So this is, you will probably have problems like this on the final exam. So think about this carefully. And it's important to master this. So practice problem. In this, I have marked phase alpha, phase gamma, phase beta, phase delta, phase epsilon, and this is a one component system, okay? one component system. So the boundary here means that along this boundary, alpha plus delta can coexist. Along this boundary, beta plus delta can coexist. Along this point over here, alpha, beta, delta can coexist over here. Along this point over here, beta, gamma, delta, and this should have been epsilon. Epsilon can coexist. What all are wrong with the above phase diagram? I want you to think about this, and we will discuss it in next class. We will start from here, and then we will do the proof of the Gibbs phase rule for general C more than one component system. So there are certain things that are right in this system, there are certain things that are wrong. Maybe one thing is wrong, maybe more than one thing is wrong. And I want you to think about this. What are the things that are wrong? Okay, good. So see you on Friday.